So to reiterate, so my objective for tonight is to review correlation, linear correlation, and maybe just introduce multiple linear correlation, linear regression, simple linear regression, and multiple regression. Multiple regression I'll just introduce a bit, and then also talk momentarily about logistic regression. Correlation, linear regression, multiple regression, logistic regression, these are really important statistical tools. They're very widely used. We're going to take a very simplistic approach to it. This is our first look at it. I know that most of you guys have not had a statistics course previously, so these are all new concepts to you. Some of you, unfortunately, because things we don't always come into these courses, with the same starting line. But I'm going to assume that for many of you that this has either been a first introduction to statistics, or it's been quite a while since you've been exposed to it. So we're going to take a simplistic look at it. By simplistic, I don't mean inaccurate or incorrect or anything like that. But I mean, I'm not going to go to real depth on it. I'm going to expose you to what I expect you to be able to use for the third exam. Hopefully, third exam, you won't find third exam too challenging. It will only cover the new material, which is basically correlation and regression. And I may also ask you a couple of questions about which statistical test that you want to apply in certain situations. The reason why I'm, in addition to linear regression, going to talk about that tonight is that many times when you guys go on to leave me behind and go on to real lives and do real things, and here I am stuck with Bio 610 again and again, semester after semester. When you guys move on to greater things, sometimes you are working on capstones, you're working on projects, you're working on research, your own research you're doing with an advisor or a professor, and you wind up collecting data. And you need to find a way to analyze that data. You need to determine whether that data supports whatever conclusions that your study is looking for. So it's important that you understand which tests, which are the correct tests to apply in certain situations where the pitfalls may be, what the assumptions are, different tests, what kind of data, different kinds of tests are intended for. So I'm gonna go over that. It's kind of like really kind of a basic review. I'm gonna go over that in addition to correlation and regression, because I think it's going to be important to you moving forward. So again, the last exam is going to be non-cumulative. We'll only cover correlation and regression, and I think we'll go through what we've seen in the previous videos, and we're going to do tonight. We'll get you through that exam, I think. And again, you'll have the same. Let me hit the mute button here. Okay, so it was muted. Thank you. If you let me know, I can mute people as they log on from here as well. So I'm going to get started with just the idea of what these different kinds of tests are. Okay, so let's presume that you may be working on a study in the future, and you may be comparing a numerical value between two groups of people. So let's say that you are examining whether a certain educational intervention, certain training or educational intervention impacts the blood sugar level for diabetics, for type 2 diabetics. So maybe you're training them on dietary choices or exercise, or you're training, maybe it's an exercise program, and they're coming in 3 times a week to exercise, something like that. But let's say you want to determine whether that intervention is helping at all. So what might we be looking at in a case like that? Well, first of all, we're looking at 2 groups, right? We're looking at, for instance, whether or not they're in the study or control. You may have a group that you are keeping as a control group that you're just tracking at the same time to see if they have any changes over the same period of time. So study and control, so this is whether or not they're in the study. So this is a nominal variable. They're either in the study group or they're in the control group. It has two values, right? So we have a nominal variable, and then you might be taking blood sugar readings on a daily or weekly basis or something like that. So we're going to take the person's average blood sugar level. So for each individual, we would have, if we look this at SPSS, we would have the study group is one variable, and that might be at either a 1 or a 2, depending on if they're a control group or the study group, right? And the other variable we're going to have is the blood sugar level that you tested at the, or maybe it's blood sugar level increase or decrease, the change in blood sugar level, and that might be -10 and +5 or -50 and -20 or something like that. So we have a numerical variable and we have a categorical variable. And our categorical variable happens to have two categories. Okay, you guys remember what test that you might use in that situation? Okay, well, we're going to compare means, right? We're going to say to ourselves, well, what's the average change in blood sugar level for the study group versus the control group? Okay, yeah, t-test, excellent. So we'll do a t-test. Now, there's a couple of variations of that t-test. One variation is when we are taking a single sample. Let's say we're only taking we're only examining the study group, and we want to know whether the study group was different from some number that we know is correct for the entire population. So we have one sample, and we're comparing it to a known mean, right? And that known mean, maybe that known mean was a blood sugar level of 127 or something like that, right? The mean for that population without an intervention. So that's one version of the t-test that we might have. A second version of the t-test is what we have right here. That's a t-test where we have two independent samples, our study group and our study group and our control group. So that's an independent samples t-test, or in other words, a two-sample t-test. And obviously, we're taking two samples. They can sample from the study group and from the control group. So there's two samples involved. So we have one sample, we have two samples, or also called independent samples. Well, because the way the t-test works, we're measuring the difference in standard errors, not in absolute values like the actual blood sugar levels, but the difference in standard errors, number of standard deviations apart that the means for these two groups are. And if they're far enough apart, enough standard deviations apart, and that's either a z-score or t-score. If the t-score is big enough, say more than 2 or 3 standard errors apart, distance apart, that would suggest an unlikely outcome if you assume them to be the same. In other words, of null hypothesis. Okay, in some cases, we might see that, well, we have two samples, and in order to calculate a standard error, we need to know the standard deviation of these two groups. Well, standard deviation of one group, the study group, might be different than the standard deviation of the control group, the other group. So at that point, we split this up into two different routes we might take. In one case, we assume equal variances, right? The variability in both groups is the same. And in the other one, we assume unequal variances. And the way that we got around this when we were calculating manually with Excel, we used the idea that the factor of 2 would determine whether or not we assumed equal variances or unequal variance. In other words, if the variance of the study group, say the standard deviation or variance, is double the standard deviation of the other or half of the other, then we would assume unequal variances rather than equal variances. SPSS does a more accurate version of this. They use that little Levine's test that you see at the front of the t-table, but it usually comes out pretty similar to that result. So we have two different versions of this t-test. Well, that's great when we only have two groups in our categorical variable. Again, categorical variable, and a numerical variable or scalar variable. Okay. So that works out great when we have either one group for single sample or two groups for a categorical variable. Now, what happens when we have multiple groups? For instance, we want to measure the blood sugar level for different ethnicities, right? So here's our new variable. So now we want to measure the blood sugar level for different ethnicities. But ethnicities, you might very well have a lot of, say, 5, 6, 7, 8, right? And then maybe 9 would be all others or something like that to just keep things under control. In New York City, in Queens, this could be 40 ethnicities or 60 ethnicities, or maybe even more, right? But the issue here is now we have more than two means that we want to compare. In other words, we might want to compare Hispanics to whites, to Asian Pacific Islanders, to Japanese, to Chinese, and so on and so forth. So we have a lot of ethnicities, a lot of means we need to compare at the same time. Well, we could use a t-test and compare one ethnicity to another, and then that same one to another, and that same one to another. But in repeating the t-test over and over again, we increase our chances of making an alpha error. In other words, rejecting the null hypothesis that there's no difference in the blood sugar level, average blood sugar level for these different two ethnicities, when indeed they were equal. In other words, saying that we reject that idea that they're equal and assume that accept that they're unequal. We don't want that to happen because that's an alpha error. That's kind of error that we don't want to make, right? Because that would imply that we've identified a difference, that we prove that our study group did better than our control group, et cetera, right? That's not the kind of error that we want to make. So in order to avoid that, we use a different test for comparing multiple averages at the same time. That test is analysis of variance. And again, you can go back over the videos for this and determine how to do this. And the way analysis of variance works is you look at the variability between the ethnicities, between the groups, and the amount of variability within the groups. And if the variability within the groups is very small, in other words, the values are all tightly close together, and the variability between the groups, in other words, the means of the groups, are far enough apart, you can use analysis of variance to prove that instead of all of the means being equal, your null hypothesis, right, etc., instead of all being equal, that at least two of them are different, right? And then once we've proved that, once you have determined you can reject the null hypothesis and accept the alternative hypothesis, then we ran post hoc tests that clarified for us which of the various combinations of ethnicity, comparisons of ethnicities, actually are different from one another. Okay, we only run the post hoc test if we could reject the null hypothesis with analysis of variance. If we didn't have enough evidence to reject it, then we wouldn't bother running the post hoc test. So that's great. So we have a way to work with numerical variables, averages, whether it's one group, one sample, two samples, or multiple groups that are being sampled here. Well, now, what about if we want to work with just categorical variables? And that comes up quite a bit. Oops, I got a spinning beach ball there. Okay, let me just see if I can't get forces to quit. Oh, I think it just woke up. Okay, let me open this again. Okay, so let's say we have categorical variables. Let's say we want to know if a certain exposure has an association with a certain outcome. So one of the possible projects that we looked at was the idea of whether if a person has insurance or not, whether it impacts whether or not they would get an influenza injection, so a vaccination. So what do we have there? We have two variables. We have the variable insurance, insured, right? And we have the variable vaccinated, yes or no. And insured, these are both, for our purposes right now, these are both yeses and nos, ones and twos. So in that case, we're comparing a categorical variable with a categorical variable and looking for an association. So our null hypothesis is that there's no association between whether being insured and whether or not you get vaccinated for the flu. Or alternative hypothesis is that there is an association. So how do we go about proving that? Well, typically the way we go about proving that is setting up a crosstabs table where we're comparing the exposure insurance, for instance, yes and no, to whether or not a person gets vaccinated or not. Vaccinated, yes. Vaccinated, no. So once we've set up that table, we can do something called a chi-square analysis. Okay, and in our chi-square analysis, what we do is, for instance, if we find in our actual sample that out of 100 people that have insurance, 50 of them got vaccinated, and out of 100 people that didn't have insurance, only 30 of them got vaccinated, right? Then we determine, let's see, 80 out of 200 people got vaccinated, right? So we say to ourselves, well, 40% of this population got vaccinated overall. There's a different rate for people who's insured versus uninsured, but now we have to determine whether that difference really is just due to chance, or is because you're really, the whole population, you really are more likely to get vaccinated if you're insured. So the way we do that is we set up another table, another contingency table, except this one, we take our values here, which are our observed values, and we create a new table called our expected values. And what we're doing there is we say to ourselves, let's say we have 100 people and 100 people that aren't insured. And in the general population, if we forget about who's insured and who isn't insured, in this population, our sample suggests that 40%, 80 out of 200, got vaccinated that year. So we would expect both of these groups to have 40 people out of 100 that get vaccinated if they're insured, or 40 people out of 100 to get vaccinated if you're uninsured, assuming that there's no difference between the two, assuming that they get vaccinated at the same rate. These are expected values. And we know in chi-square what we do is we take the difference between each one of these boxes, our expected value, the observed values minus expected values, square that, then divided by expected values, do that for each of the 4 values, and then we add them up to get a chi-square value, right? So that chi-square value tells us, if it's large enough, it tells us that, in other words, if it exceeds the critical value for chi-square, it tells us that we can go ahead and reject the null hypothesis that there's no association between these 2 variables, and accept the alternative that there is an association. We also can calculate something called a relative risk and an odds ratio. So if we look at this, the risk of getting vaccinated if you're insured is 50 out of 100, or 0.5. The risk of getting vaccinated if you're uninsured is 0.3. So 0.3 over 0.5 is 1.67. So you're 1.67 times as likely to get vaccinated if you happen to be insured. And we have another measure besides that's called the relative risk over risk. The other measure we have is the odds ratio. The odds would be 50 over 50, which would be 1, 30 over 70, which would be, I'm going to just estimate that as, let's see, it's going to be 0.4, let's say, for argument's sake. I don't know what it is, and it comes out to 1.5. That's our odds ratio. If our confidence interval for those 2 numbers excludes 1, right? What we would expect if there's no difference, we would expect this ratio to be the same. In other words, 40% over 40% would be equal to 1, as it is in expected values. So we could reject our null hypothesis that the odds ratio is equal to 1, and say that we can accept the alternative hypothesis that that you're 1.5 times as likely, the odds are 1.5 times as likely that you would get vaccinated if you're insured. So we can use this to evaluate categorical and categorical variables associated between categorical and categorical variables. So these are important tools. So we have these tools there for specific application, specific situations where you're dealing with certain kinds of data. Okay, now, again, this is the reason why I'm bringing this up is because as you move forward, at some point, you're going to say to yourself, I need to do a statistical analysis and I need to figure out how I'm going to handle this particular kind of data. So you want to look at the data type, and then you want to evaluate, well, what test, what statistical analysis, what test do I apply to this particular data? So what I really would expect you guys to do, which would really help yourselves out, is before you even start collecting data, before, for instance, if you're formulating a survey, if you're putting together a study, right, before you even get to that point, you might say to yourself, okay, now let me imagine myself at the end of this study, and I've collected this data. What kind of variables do I have? What kind of numbers are these? How am I going to do, what kind of analysis am I going to do on this data? That will help avoid painting yourself into a corner where you collect a lot of data, but it may not be really what you need to demonstrate the relationship that you want to show. So think about the types of data you're working with before you even start collecting it, and what kind of analysis at the end of the day, what kind of analysis you might have to apply to that data. Okay, so I talked about nominal data, categorical and numerical data. Nominal data with more than one sample, and numerical data. Nominal data and multiple means or multiple values for categorical variables. I talked about nominal variables and then associating with other nominal variables. What did I leave out? What combination of variable types have I not spoken about so far? Okay, I'm going to wait for you to guess because it's going to be our next topic and our main topic of the evening. Shouldn't be that hard. Why are we all here tonight? What's going to be on exam 3? Come on, somebody be bold and type something into the chat box. Let me make sure we're muted again. Yeah, we're talking about correlation linear regression. But the important thing here is that's the test that we're talking about. The important thing here is that what we're looking for is an association between two numerical variables. We haven't examined that at all. In other words, we talk about categorical and numerical, categorical and multiple categories, and numerical, categorical, and categorical. We haven't talked about what about when we have an example of two different kinds of numerical variables, and we want to show that there's an association between those two sets of variables. Okay, and that's what correlation and regression are all about. So I'm gonna start with a data set that we can look at and discuss. Okay, in this data set, I'll upload this later on. So if you want to play with it, you can do that as well. And here it is, exam revision.sav. I found this somewhere. And we're going to look at the variables that are on here. If SPSS ever cooperates and opens up, is it bouncing up and down? I double clicked it. Let's see. What's that? Up there it goes. Okay, I'm in an unair-conditioned room here, and it's upstairs, so it's pretty hot in here. So if I sound sweaty, it's because I am sweaty. Okay, let's see what we got here. Okay, so this one, it opened up a blank page, so it didn't open up the one. Oh, here it comes, it's loading now. Oh my goodness. It's giving me some great news. Yeah, that's the first time that's come up. Oh, by the way, in case that comes up for you, you may have noticed your license will expire in 30 days. That's the first time I've seen this, I think, so far with the version I have installed right now. That will, the SPSS will let you continue to use the software for 30 days after the expiration date. So the first time you see that, and you can actually go into the license, I think, and check. Let me see if I can't find it. Support. About SPSS. Let's see if it's got a date in here. I don't see it. You may have to go into the license file to see it. Oh, actually, you want to know something? I think there's a command you can type in that tells you when the license expires. Okay. Let me see. Right. Nope, apparently not. That's not working. Land license, yeah. I think there is a command you can use to, you can probably Google that, but at any rate, it gives you 30 days from the first time that you, typically first time you see that, which is that the actual expiration date. But I'll find out. I'll post on Blackboard if any of you need to know when that's going to expire. Okay, so at any rate, I don't need the syntax window anymore. Okay, and again, that syntax window is a window where you could type in commands and operate SPSS from a command line, or actually generate programs to do repeated analysis. Okay, so at any rate, let's see what our variables are here. Our variables are a score, which is the score on an exam that students are taking. Hours are hours spent revising, or in other words, studying for this exam. Okay, maybe over the course of a month or something like that. Maybe it's a presentation of some kind, maybe it's a capstone. Okay, the third variable is anxiety, and this anxiety score is level of anxiety about taking this exam, and 8 points is a entry level score, like for instance, maybe PSA test, maybe predicting how well you do on the SATs, for instance, or some other, like a pretest, like very frequently, you may take a standardized exam, and as a study guide, they'll give you a 20 question sample of what might be on that test. So it might be something of that nature. Okay, so all of these things are numerical variables. If I go back, their scores are numerical variable. So for individual number 1, by the way, it's a relatively small data set for regression. Okay, usually with regression, you're usually dealing with much larger data sets than this, but this will do for our purposes. Okay, so this first person, each one of these is, well, rows represents a subject in this study. Okay, so this first person, their score was 62 on this test. They spent 40 hours during the previous month studying or revising their work for this test. Their anxiety level, and this is a scale, I'm not familiar with what the scale is, but this is a scale that measured how anxious they were. Some were more anxious than others, 61, 58, so on and so forth. And the last value is the score that they had in a pretest. How much did you know about this stuff before you even started, let's say? And each one of them had a different score. Okay, so what we're really interested in here, we're interested in seeing what the association is between what a person might score in an exam and how many hours they might spend studying, what their anxiety level is, and how much they knew going in. And each one of these variables are numerical variables. This is the first time that we're looking at something where we don't have any categorical variables at all. So I'm just going to look at the first pair of variables here, score and hours of study. And I want to look to see if there's an association, a correlation. So from now on in the future, when you're talking with friends and you want to say, oh yeah, that's this, I always seem to see this happen with something else. Call that an association. Do me a favor and call that an association. So now if you use the word correlation, I want you to think statistics. Okay, so correlation is a special thing for us. It's a mathematical calculation that estimates how strong the association or correlation between two numerical variables are. So the first way I might want to take a look at this is to look at it graphically. So I'm going to plot this, and since these are numerical variables, I'm going to say that that this represents two values on a point on a graph, an XY graph. Okay, this might be the x-axis, this might be the y-axis. So I'm going to give that a try and plot those two variables. I'm going to say graphs, legacy dialogues, because I'm old and I am a legacy. Okay, and I'm going to say scatter plot. Okay, so I'm going to go into the scatter plot. Now, notice I said, is there an association, right? I didn't say, how does hours predict score on an exam? I'm not at that point. I'm just looking for an association of any kind. I'm not looking to predict one thing from another. I just want to see if there's an association. So as far as correlation is concerned, it doesn't matter which of these we put into the x-axis and the y-axis. That will change when we go to regression. Regression is something that we use predictively to try and predict what a person's score might be based on various devices that he might, various other measurements that we might have for that individual. Okay, so I'm just going to move in exam and hours into the x and y axis. And I'm going to click OK. That's all I really need. I don't need to put titles in it and so on and so forth at this stage. I'll click OK. And let's see how this looks. Let me look at it graphically. Okay, should be a graph coming up here pretty soon. Here we go. Okay, so let's see what we have here. We have, in the x-axis, we have the hours spent studying or revising. In the y-axis, we have the exam score, the student's score. So if I look at this, it really seems like the less time you spend studying or the more time you spend studying, it affects what your score is. And it looks like the more time you spend studying, the higher your score is going to be. Okay, that's called a positive correlation. As one variable goes up, the other variable goes up with it. That's a positive correlation. Okay, I can actually ask SPSS to take this graph. I'm double clicking on it, and it should open in a new window. And I can ask it to create a best fit line for me. Okay, I'm just going to say there. Okay, should let me talk this. Hold on. Oh, it already drew it. Okay, I'm sorry. Drew it in the background. I didn't need to do this anyway. Okay, so we have, when I close this, it'll actually update the chart in the output behind me. Okay, so we see this line that SPSS has calculated to be a best fit for all of these different coordinates. Okay, each one of these dots represents a single subject. So for instance, this subject had a test score of 56, and he spent 26 hours approximately revising or studying for this exam or this presentation, right? So this person spent almost 50 hours, and their score was 82, right, on this particular exam. So we can see there's an association here, and this line, I can see that roughly half of the people are below and half of them are above. Very few people actually land right on the line that represents this, right? So what's happening here is SPSS has balanced the total squares of the differences for the people that are above this line and the total squares of the differences for the people that are below this line. In other words, the distance from the line to each one of these values squared is balanced on both sides. Okay, it does that calculation for us, and that's basically what this line represents. So number one, I see from this line that it's a positive correlation. As the hours go up, the exam score goes up as well. Okay, had it been sloping downwards, that would have been a negative correlation. As the hours went up, the exam score went down. I just want to show you that it doesn't matter. It doesn't matter what which variable you put into the x-axis, which one you put into the y-axis. You will still get the same relationship. Now, the scales may look a bit different, right? If you stretch it out or make it narrower, okay, the scales themselves could make things look a bit different. So I'm going to put that up there. I'm going to put this down here this time, but you'll still see it'll show a good, a nice positive correlation. See how scales look different in this case, but it's still the same correlation. Okay, so now we want to describe this numerically. We want a number that we can use to describe this association. Okay, and that's going to be what we call correlation. So I'm going to go up here to Analyze, and I am going to go down to the test correlate. And our choice is going to be bivariate. Bivariate because we're only looking at two variables at a time. So it's a bivariate correlation. And the two variables I'm going to look for are exam score and hours spent studying. Now notice that it waits for me to put both variables in. It doesn't ask me which one's the top variable, which one's x, which one's y. It doesn't care about that. Just looking for an association at this stage. One of the calculations it's going to make is the Pearson's R value. Okay, Pearson R or rho for the entire population R. That is a numerical representation of the value of this correlation, how strong this association or correlation is. So I'm going to click OK, and it will calculate the correlation coefficient. And let's see what I wind up getting. Okay, so now it actually calculates it. It looks for the correlation between the exam score and the exam score. Exam score, that's going to be a correlation of 1. The exam score and the exam score is the same for each individual person. That really doesn't tell us anything. But when I look at the correlation or association between exam score and the hours spent revising, look at this, it's 0.821. Okay, this just repeats that again. Hours spent revising and exam score, 0.821, same value, right? Just like our drawing the graph two ways. Okay, so 0.821 is our important number here, right? Significance is important also. It tells us that this is statistically significant, but our real number that we're interested in here is 0.821. The correlation coefficient can have a value between -1 to +1, going right through 0. 0 suggests that you have no association between the correlation between the exam score and the hours, right? So that would suggest that, gee, we can stop right here. There's no association between this. One does not affect what the other one does. So for instance, if I were to look for an association, the correlation between, let me think about this, let's see, between the gas mileage in a car and trying to think something that definitely will happen. That'd be very likely to happen. The gas mileage in a car and the price of the car. For instance, there may not be an association between them. There might be inexpensive cars get poor gas mileage, might be expensive cars get poor gas, and good ones, and so on and so forth. There might not be an association between those two. But if I looked at the correlation between the gas mileage car gets and the weight of the car, wow, that's probably has a correlation. That probably is an association. And chances are it's a positive correlation. As the weight, a negative correlation. As the weight goes up, the gas mileage goes down, right? So we can look at that. So what we're looking for here is that this is different than 0. So our null hypothesis here is R is equal to 0. Pearson's correlation is equal to 0, that there's no association. In this case, our R value is 0.821. It's a positive number, so that would suggest that there's a strong association between the exam score and the hours spent studying. Now, that at 0.821, that's exceptionally high. We don't usually see that too often when we do correlations, but it's fortunate for this example, we're getting to see that. Right? You'll notice correlation is significant, 0.01 level, so that's a 0.01. So this tells us that there is an association. So the closer this is to 0, the weaker the association. Now you could have a correlation which is 0.2, right, which is pretty close to 0, which is a much weaker association. The dots would be way more scattered than this, right? So that would be a negative association, right? That would be a poor association, but it still might be statistically significant. It's just that it's not as good an indicator of what the exam score might be. Right? And that's more important to us when we get into regression. So the closer this is to 1 or -1, the stronger the correlation between these two variables. Okay, so questions so far? Just on that part right there. Do I have any questions on that? Okay, before I move on. So then I got to move on. What are the numerical cutoffs for a weekend? You know, there really aren't. I think once you get under, say, 30%, 0.3 or something like that, it's a pretty weak association. That doesn't mean that there's no association, just means that it's weak. In other words, that could still be statistically significant, but it's just not as good a predictor. There's a lot of variability between the one numerical variable and the other numerical variable, but there is some association there. Okay, and I got a question mark there. I'm not sure what the question mark is. I need a little bit more than question mark. I'm going to assume that the question mark means that we're a little bit confused, that we're not that sure about it. So why is it weak? It's stronger if it's closer to 1. If it's smaller, like 0.3, that would mean like 0.3, 0.2, 0.1, closer to 0. That would mean that it's not as strong an association. Okay, and if it comes out 0, that would suggest that there's no association. If it comes out 0, so our null hypothesis here is R is equal to 0. There's no correlation, no association. And we come up here with our R actually is equal to 0.21 for our sample, right? And our significance is less than 0.05. So we can reject the null hypothesis that R is equal to 0, no association, and accept the alternative hypothesis that R is not equal to 0, that there is an association. In fact, it turns out for our sample it's equal to 0.821. Since null hypothesis is 0, we fail. No, in this case we reject, right? Because the significance is, first of all, number 1, this is much different than 0, an R of 0. Our R here is 0.821. It's really close to 1. Okay, and our significance is greater than, less than 0.05. So that means we can reject our null hypothesis and say that R is not equal to 0, that there is an association. In this case, it happens to be a positive association. Okay, so now how can I put this to work for me? How can I do that? Now I'm going to go into regression. In regression, we now want to quantify this effect. We want to know, can I take the number of hours a person studied and predict what their score is going to be? This is kind of a silly example. I mean, really, we wouldn't be that worried. We tell somebody, hey, study hard and you'll get a better score. And that would make sense to and so on. Really, I don't think we would really necessarily focus too much on exactly how each hour of study might affect you. But that's what we do in regression. And while it may be kind of trivial here, there may be studies, for instance, where you're doing an intervention where you want to know, well, what's the impact of me changing the amount of the dosage rate of vaccine the dosage of antibiotic I have to the effect it has on a patient's viral load or something like that, antiviral versus their viral load in their body. What's the effect there? And in that case, we really want to know how to quantify that, because we want to be able to predict that if we give this person this much of this antiviral, that it will lower their viral load by this much. So we can make a balance between the side effects of the drug and the effects of the drug. So there are times where we're going to, or if we have an intervention that's going to cost money, a training intervention or a educational intervention we do as public health workers in the community, we want to know, well, for every hour a person attended these sessions, how much did that impact on their nutrition, on their BMI, on their level of exercise, and so on and so forth. So we want to see if there's an association, and predicting it in those cases is important because it costs money to do the intervention. So you want to know what kind of result you get from it. Okay, so let's go to regression. Let's go look at the same thing from the perspective of regression. I'm going to go to Analyze, and I'm going to go to Regression. Okay, so now a couple of versions of SPSS. In the versions, in the least expensive version, which was, I think, the base version, okay, when you go into regression, you will see linear, but you won't see logistic. Okay, so I'm going to stick for the most part to linear regression. I'm just going to mention logistic regression. If you guys have the lower, you won't see that if you have the lower end version of it. The standard version, I don't know, the versions, probably the $35 version versus $50 version, will have the more expensive will have binary logistic. But I'm just going to mention and introduce the idea of logistic regression and explain like what it means, what it predicts, what we use it for, but not necessarily. It won't be on the test, and it won't necessarily be something that you're going to be graded on or have homework on. However, I will say this, that for those of you that are going to go into advanced courses that are going to involve statistics, maybe you take a more advanced statistical course, like one of the other statistics courses they offer here, it may be worthwhile. That logistics regression is going to be an important part of those courses. In fact, they have whole courses on regression, right? And binary logistic regression will be one of those areas that they may concentrate on in an advanced course. Helps pays to know what it is, right? But for our purposes, we're just going to define it rather than, or contrast it to just regular old linear regression. Okay, so regression, simple linear regression. That's what I'm doing here. I'm looking to predict, to be able to draw a straight line which represents the relationship between the exam score and the hours of training. Okay, so here we go. Except this time, it matters which one we call the x-axis and which one we call the y-axis. So the x-axis, the independent variable, and the dependent variable. In other words, this is the variable that's the predictive variable, and this is the variable that, based on changes here, what we expect, this is going to predict what this variable is. So this is going to be our x-axis, this is going to be our y-axis. So which variable is the independent variable here? Well, the hours spent studying goes in here. That's going to be our independent or predictive variable. And what are we going to use that to predict? We're going to use that to predict the person's exam score. Okay, I wouldn't do it the other way around. I guess you could, it's kind of like behind the curve. In other words, the person takes the exam and then you're interested in how many hours they study. Not so much, right? You'd be more interested in knowing, well, if he studies this many hours, what does that mean? Or how likely is what was the exam score going to be, right? So this makes more sense. The independent or predictor variable is hours, and the dependent or predicted variable is the exam score. That's what we're trying to predict. Okay, so I am going to, I'm going to leave this on method enter. There's a couple other choices here. Mostly these others are for something called multiple regression, where you actually may look at more than one variable at a time. We may get to that in this, if we have enough time. So I'm gonna let's leave this just the way it is, and I'm gonna click OK. I'm gonna come back here and say do some other things, but I'm gonna click OK here. Okay, so SPSS is gonna do an analysis for regression, and the first thing we're going to see is we're going to see a model summary. Okay, and in this model summary, it's going to recalculate the correlation. Remember our correlation, there's a correlation right there, 0.821. Okay, so 0.821 is our correlation. It does something interesting then. It takes our correlation, just recalculated, same way it calculated before, takes that value and it squares it. 0.821 times 0.821, calls that R squared, 0.674. Okay, so it also calculates this thing called adjusted R squared. This has something, this adjusted R squared is corrected for certain kinds of situations where, especially when you have multiple regression and some of the variables that you use against predictive variables themselves have a strong association. So maybe they're not, in other words, that they're not the best choices, and this will change because of that. Sample size has an impact on that, and so on. But I wouldn't worry about that for our purposes. We're just going to stick with the value R squared. Okay, so what does R squared mean? R squared is based on the correlation, right? The higher the correlation is, the higher R squared value is, right? That number is 0.67. That tells us how much of the variability, how much of the value of the exam score can be attributed to the hours spent studying. So this is a pretty significant effect, isn't it? 67% of how well you do in the exam, your exam score, can be predicted using the hours how many hours that you study. Wow, that's pretty impressive. On the other hand, it means that 33% is based on 33% of the exam score, variability exam score, is determined by other factors other than how much you studied. We saw some of them. How much you knew when going in the exam A score, and your anxiety level in test taking. Those are all things that are going to impact this. We're only looking at the one variable, the hours spent studying right now. Okay, so let's take a look at this. Is there R squared value generally considered significant in terms of the contribution? That's a good question. Again, that's kind of a judgment call, but I would say that anytime you get anything over 30%, you're doing pretty good, right? Under 30%, then it's basically what you're saying is that this has an influence on the exam score, but there are other variables, other things happening that have an even bigger influence than the particular variable that you're looking at. So once you get under 50%, once you get under 30%, I would say that you start to be a little bit disappointed that you really, it's not going to be as good a predictor as you would like it to be, right? But it isn't like there's a single number that everybody agrees on. So it's not going to be like 0.05 or something like that for alpha. Okay, so let's take a look at this. The analysis of variance is a test that actually tests the statistical significance of this regression, of this association. So our main concern here is that we see that it is statistically significant, that this is less than 0.05. And then finally, we go down to the actual coefficients, the actual part of this that tells us what the association is mathematically, how the association works in terms of the value of one predicting the value of other. You may remember we mentioned that this is called linear regression. We're assuming a linear association between the predictor variable and the predictor variable and the predicted variable, the y and the x. Okay, so now I just want to remind you guys a little bit of your old algebra. Okay, and this idea of a line. In other words, we want to create a line. I'm going to make an X and a Y axis here. We want to create a line, right? Here's our line, that represents the best fit that we were looking at. And we want to know the formula for that line. When we know, well, Y is equal to, when we're in algebra, when I took algebra, you said MX plus B. I think most of the texts now say Y. For statistics, say beta X plus alpha, right? I think, or A, right, like later, or B and A, right? So what is the M or the beta here? What do those things represent? You guys remember? That represents the slope, exactly. In other words, it represents the change in Y over the change in X, right? So that represents our slope. What about this other thing, this plus B or this plus alpha? What does that represent? That represents, well, let's say Y is equal to BX plus A. If X is 0, that drops away. Y is equal to A. So in other words, when X is equal to 0, this crosses the y-intercept. This is the value of y when X is equal to 0. Okay, that's also called the y-intercept. Okay, so if I know the slope, and if I know the y-intercept, in other words, I know this beta and this alpha, if I know those two things, I can create a line. I can draw this line. I know this line, exactly where it's going to be. Excellent, intercept. Okay, I know exactly where that's going to be. So that's what we're going to do here. We're going to go back here. We're going to take a look at these values. And this value, hours spent revising, unstandardized coefficient, okay, that hours spent revising is represents the slope for our line. And constant represents the y-intercept. So essentially, the formula that represents this relationship between hours and our predictive variable, exam score, then be y is equal to 0.992. Remember, that's the slope, x plus the y-intercept, which is 22. I'm just going to call it 22. Okay. So actually, I could even just call this 1 maybe. Just to make things simple, I'm going to call this 1. 1x plus 22. Okay, well, what do y and x really represent? Y represents the exam score is equal to 1x plus 22. And x is what? Hours. 1 times the hours plus 22. Okay, so we might actually say to ourselves, well, let's predict if someone says, I plan on studying for 35 hours, what do we think their exam score is going to be? Hours times 1, 35 times 1 is 35, plus 22 is going to be 57. Right? So we would predict that their exam score is 57. So that's basically one of the things we're interested in. And the other thing that we're interested in specifically is this slope. Now that we know the slope is 1 to 1, we can predict for every hour of extra time you spend studying, you will get paid off by an extra point on the exam. Okay? And so you can make a trade-off. How good, I guess, right? How important is it to get to a certain score? You know, it would be wonderful if it was this predictable, right? So at any rate, but that's what we're after here. We're after using our understanding of correlation now to define a line, a straight line, which estimates the relationship between these two variables. And then we can use the slope in that line to predict how one variable impacts another variable. Okay? I just want to show you one other thing that we might want to do with this. I'm going to go over here to analyze. I'm going to go back to regression, to linear regression. And I'm going to go in here to save, right? I'm going to go in here to save, and I'm going to say save the residuals, the unstandardized and the standardized residuals. I'm going to click continue, and then I'm going to click OK. Okay, now SPSS go do our calculation again, and we got basically the same thing we got before. We got an extra box down here. Residual statistics, predicted values, residual values, minimum, the average, predicted value, in other words, the average exam score, the average residual value, the average is 0, and that's half above, half below, so on and so forth, the standard deviation. Well, what are those numbers? Anyway, what are we talking about there? Well, if we look back here, and this is something we haven't seen before, we look back at our data set again. Now, there are two new variables here that weren't here before. One is the residual value. One is the residual value. I think I chose the wrong thing here. I'm going to go back to analyze this to regression, linear, and I meant to pick off residuals unstandardized and predicted values standardized. What I did there was I told it to give me the residuals, unstandardized and standardized. I'll talk about what that means in a second. Let's do this again. It's going to create two new variables here. Here we go. Okay. And let me see. Let's see. Okay, go back to our data file. And here are our two new variables. I'm going to get rid of these two just so I don't confuse you. Okay, these two new variables, the predicted value and the residual. Okay, so what does that mean? The predicted, and these are the unstandardized one, right? Forget about that. I checked off standardized a second ago. Okay, the predicted value is if we applied the formula to these two numbers, if we applied the formula to 40 hours, we would have predicted that that person would have gotten a score of 61. If we had applied 31 hours to our formula, we would have predicted this person would have got a score of 53, et cetera, et cetera, et cetera. Okay, so these are all the values that would be that we would have predicted if we applied our formula. And if I look back here, I can actually look here and see how well I managed to predict this. This person, we said 62, and boy, we came really close on that person. This person, we said 72, but he only got a score, and he got a score of 82. So that was a much bigger difference. In fact, the next column is the difference. And if you look at it, it's the difference between the predicted value from our formula and what the person actually got. Okay, so for instance, this person over here, let's say this one, this person, the difference was -4. So in other words, we got 59 versus 55. So his actual score in the exam was 4 points less than we had predicted. Okay, so we got our predicted values is what we would have calculated that person would have gotten based on our formula, and our residual values are the amount that we were off, the error, how far we missed for each individual person that actually did this. Now the standardized, one of the things we're interested in to make sure that, we want to make sure that these values here, that these values are normally distributed. We don't want to see that for people who studied more hours, that our residual values were smaller. We were a better predictor at one end than we were at the other end. So we want this to be basically normally distributed. In other words, no specific pattern that would suggest that this is somehow or other skewed. So and one of the ways we could do that is to actually look at the, let me go back here, analyze, regression, linear. We can actually go back here and we could ask it to calculate the standardized values for these, for the predicted values and the residual values. We're taking the values for the exam scores and the values for the residuals, the error that we have, and we're asking it to recode them into the z-score for each value that we're looking at here for residual. In other words, we would expect the z-score to, more of these to be near zero, and fewer of them to be very large or very small, just as we would expect any normal distribution. So that makes it a little easier to kind of evaluate if there's some unusual pattern going on. So I'm not going to be too concerned about, for our purposes, I want you to be more concerned about the values that we're calculating for residual. I don't want to confuse you too much at this stage. Linear regression, let me see if I can't also do some graphs, plots. Okay, so Z predicted, or Z residual. Let's see what we wind up with there. Okay, so in this case, we don't want to see any particular pattern here. We don't want to see an association where, like at this end, we have all low values, at this end, we have all high values. We don't want to see a specific, we want this to be relatively random, that there's no particular association between the Z value for the residual and the actual predicted value. Uh-oh, I think I crashed. I think SPSS crashed there. Okay, so I wouldn't worry about that too much. I don't think I'll be concentrating on that on the exam at all. Let me get this opened again. Oh, I still got my mouse. Okay, again, I think I'm starting to overwhelm you a bit, so I want to scale back a little bit. Now, the next thing I want to do is, so really, for the exam, what I would expect that I would want you to be able to do is, number one, run a correlation, determine the Pearson's R value, look at the significance, determine whether, state the null hypothesis, R is equal to 0, R is not equal to 0. Tell me if you can reject the null hypothesis, which is significant, has to be less than 0.05. It even says, I think, on the box for correlation. And then for a regression, to identify what is the predictive variable, what is the predicted variable, and then to turn the regression into a formula. In other words, write out the formula, y is equal to beta x plus alpha, the slope and the y-intercept, and maybe even convert that into the actual values that are in there, the exam score in the hours, instead of y and x. And maybe actually ask you to do a calculation that if a person spends this number of hours running or studying, what would you predict is the value you would get on this exam score, or whatever the similar example is. So I might ask something relatively simple like that. Okay, so that is regression. That's correlation. I might ask you to identify when you have a positive correlation, when you have a negative correlation. So, for instance, let's just take a look at that. So let's say that we have something that looks like, whoops, I didn't mean to do that. Pen thinks you want to draw lines here, so I'm going to get rid of this. Okay. Okay, so here is vehicle weight, and this is mileage. Okay, let's say we have, there's a car there, 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 there's a car there. Okay, what would we expect this line to look like? It looks like there's a correlation here, right? So for instance, the best fit line might look something like this. Okay, so what do you think the R value would be here for correlation? Is it going to be 0? Or is it going to be closer? Is it going to be a positive number? Or is it going to be a negative number? Negative, right? Because it looks like a pretty good correlation. but it's going to be a negative number. Okay, would you say it's going to be equal to negative 0.1 or negative 0.9 or negative let's say 8? Then they're too close together. How about that? Negative 0.8. Negative 0.1 or negative 0.8? Yeah, I think so. Negative 0.8 also. It looks like a pretty good correlation. If it had been like something like this, right, then that might have been like negative 0.1. Now, how about this one? Okay, and this one I'm going to say is, okay. Okay, let me see. R equals +1, R equals 0, R equals negative 0.7, R equals positive 0.7. What do you think on that one? Right, positive 0.7, right? It's a strong correlation, it's pretty close to the line, right? And it's as one variable increases, the other variable increases as well, right? So that's the way we would look at the R value. Okay, and our null hypothesis, when we do this kind of analysis, R is equal to 0. In other words, we're starting with the assumption that there is no association between these two. And our alternative hypothesis is R is not equal to 0. Because we don't care if it's a 0.1 or 0.7 or 0.9, we reject the null hypothesis. All we care about is it equal to 0 or not. So if we get we got an R value of 0.9 and significance of 0.008. Can I reject the null hypothesis? Can I say that I have a correlation there? What's the significance? Right, the significance for the R value is 0.8. Is that less than 0.05? I know I fooled you because I made this seem like it was such a strong association, but we don't have that. Maybe the sample size is too small for us to be sure that we didn't get that by chance. So in that case, we can't reject the null hypothesis. But had this been 0.04, then we would be able to reject the null hypothesis. Well, how about R is equal to negative 0.15, and the significance is equal to 0.001. Can I reject the null hypothesis there? Yes, I can, because the significance is less than 0.05. I can reject the null hypothesis, accept the alternative hypothesis, right? It is true that it's a weak association, but it's statistically significant. It's real. It's not due to chance, right? Even though it's a weak negative association, not very predictable. Okay, so let me talk about this idea of multiple regression and multiple correlation and linear regression. Okay, so let me get rid of this first. Now you'll notice that there's other variables here: anxiety level and this access level points, entry level points. In other words, maybe a pre-test or something like that, something that tested how much you knew going in. Okay, so let's take a look at the scatter plot for the score and anxiety. I'm going to look at the graph, legacy dialogues, and go to Stata. Let's see how strong is the association between the exam score and the level of anxiety. Let's put the exam score in there. Let's put like an anxiety level in there and click OK. And let's see what kind of thing we get. See what this thing looks like. Oh, there's the background there. Oh, nope. Where'd it go? There's my output window. Okay, there we go. Well, let's see. Wow, that doesn't look very good, does it? Now let's double click on this draw line. See if it comes up with a line for us. See how the line looks. Yeah, well, it doesn't look like much, right? Now notice this, that a flat horizontal line is an R value of 0. Why is that? Well, a flat line tells you that no matter what the anxiety level is, that you have the same exam score, right? So if it's dead flat, that suggests that you don't have a correlation. The dots are so scattered And this is so flat that I don't see anxiety having that much of an influence on this particular exam. Okay, let's actually do a correlation. Analyze, correlate, bivariate. Okay, and I'm going to move in there exam score and anxiety. And let's actually calculate the Pearson's R value. Remember, our null hypothesis, R is equal to 0. Let's see what we got. Okay, look, just like that graph, it shows a slight negative correlation, negative 0.118. Is it statistically significant? Oh no, it's not less than 0.05, so I failed to reject the null hypothesis. So in fact, I don't know that there is an association at all here. I don't have enough statistical evidence to say with less than 5% chance of being wrong that I can say that that the null hypothesis is not true, to reject the null hypothesis. So I failed to reject the null hypothesis. So that doesn't seem to help me very much. Let's take a look at the other variable that's there. Analyze. Where is it? Correlation, bivariate. Let's take a look at, let's get rid of anxiety here. And let's look at the entry level score. Okay, how much you knew going into the exam. And see how that affects your, if there's association there. Okay, oh well, look, that's a very strong association also. And we also see that the significance of 0.000, I can reject the null hypothesis, R is equal to 0, and accept the alternative hypothesis that there is an association, a correlation between the entry level points and the exam score. Okay, so that's point, and it's a strong association. So let's see what I can do if I look at both of these variables at the same time. If I see if I can't make both of these variables work for me at the same time. So I'm going to go into regression, and I am going to look into linear regression. And this time I'm going to put my dependent variable as this exam score. That's the predicted variable. But into the independent variables, I'm going to put both hours of study and what the entry level score was. I'm going to leave the method enter turned on here for our purposes. I'm going to click OK. It's just a demonstration. I may not ask you this on the exam. Let's take a look at what we get now. Well, now I get an R value of 0.912, an R square of 0.832, adjusted R square. Now remember, this looks for, it's impacted by small sample size or large sample size, but it's particularly impacted by if there is some association between these two values, these two variables that I'm using as predictive variables. In other words, hours spent studying and the entry level points. If those themselves are very closely associated, well, it's kind of like cheating, right? Because they both kind of give you the same information if they're really very closely related. So that will impact what that adjusted R square value is. For our purposes, I'm going to stick with the R square value, not the adjusted R square. So what does this tell you? This tells you that when I employ both variables as predictor variables together, I have a much better chance of predicting what the person's exam score is going to be. Now I've accounted for 83% of the variability in the person's final exam score, rather than before. I think it was 60 something percent or something like that, right? 0.8 times 0.8. I think it was before. So now this seems much better. But now, how do these coefficients change? Well, now this formula is, now I have two slopes that contribute here. I have the hours spent studying, and I have the entry level points. Okay, so our new formula for our multiple regression is going to be y is equal to beta 1x plus beta 2x plus our y-intercept. I'll call that alpha. I'm not sure what notation the book uses. I don't remember. But I'm not too concerned about that. I'm more concerned about applying this correctly to create a formula which predicts what our values are. So, okay, so y is going to be equal to, let's see, what's our first unstandardized coefficient? It's going to be, for hours, it's going to be 0.476 times x, plus for entry level points, it's going to be 1.99. 1.99. I'm sorry, this is x1, x2, plus our alpha is negative 3.9. Negative 3.9. So our final formula is going to be y, or in other words, let me undo that. Okay, final formula is going to be our exam score. We predict is going to be equal to 0.476 times the hours that are spent studying, plus 1.99 times our entry score, minus 3.9. And that formula is going to be our formula for our multiple regression. And that one appears to be a better predictor than when we just looked at hours and exam score. Okay, so that's what multiple linear regression does for it. It allows us to build in more than one variable, more than one predictive variable into our equation. I won't ask you to solve a multiple linear regression problem on the exam. Well, how about logistic regression? What's this thing called logistic regression? Let me close this, get it out of the way. And I just want to introduce logistic regression. I may give you some links for those of you that may be moving on to more advanced courses. Some links, or maybe I have a recording of a video that might be useful to you, that like you can maybe after you're done with the exam, or after you've gotten this course, all your course requirements, all the homework's done, all the other stuff, you might want to just chase that down and take a look at it. So what is logistic regression? In this case, it's called binary logistic regression. Okay, so what is that all about? Well, first of all, let's look at binary and logistic. What do they mean? Well, logistic is, remember the Venn diagrams and some of the other logic stuff that we looked at? Logistic usually means, like, true or not true. True or false, on or off, diabetic, not diabetic, right? So we're looking at, when we look at binary, we're only looking at two outcomes: true or false, yes or no, diabetic, not diabetic, and so on and so forth. So that's what we're talking about when we talk about binary logistic. A yes or no to some variable which has two values. Did you get vaccinated or did you not get vaccinated? Did you get the flu? Did you not get the flu? And so on. So in regression, we're looking at trying to predict this using other predictive variables. So basically, unlike a linear regression, where we were comparing two numerical variables, right? And we were looking for a score that we wanted to predict. And we were using two other variables, two predictive variables, hours. I'll just stick with one predictive variable, to help predict what the score is. One numerical variable to predict what another numerical variable value is going to be for each person that I knew the hours for. Right. Well, in this case, I'm looking for a binary outcome. So for instance, I might be interested in what's the probability that a person is diabetic in a population, and what might influence that. Let's see, what would that formula be? The probability that they're diabetic might have something to do, let's see, some value times, let's say, what might influence that? Their BMI. Well, what else might influence that? some other factor times how much exercise they get. And another factor might be numerical variables. Another factor might be their age, another numerical variable. But you can also include in this categorical variables. Are they male or female, right? So you can use these numerical values and categorical values to help you predict the probability that someone is diabetic. So when you create your regression formula in logistic regression, what you're going to wind up with is you're going to wind up with a probability that a person is diabetic based on what their BMI is, how much they exercise, what their age is, and whether they're male or female. And each one of these will contribute to that. And then finally, for any particular person, maybe the probability that they're diabetic is 10%. Or maybe if you got different values, probability they're diabetic is 5% or something like that, right? So that's what when we talk about logistic regression, particularly binary logistic regression, we're looking to, instead of predicting a specific score or value or numerical value, we're looking to predict what the probability of a person that meets these, that has these various other values for other variables, what their probability of being diabetic, being having heart disease, having coronary artery disease, so on and so forth, what their probabilities for all this stuff are. Okay? So I think that's as much as I want to broach on logistic regression. Okay, so I know that for many of you this is the new stuff, and this is a 5-week course, and boy, I wish we could do this again in the fall, and all of us will be together for 16 weeks, and we can have a great time. And what we did, and the stuff we did 3 times a week, we could have done once a week. Spent a whole week on what we spent trying to get through in 1 week for this, literally. Since it's a 15-week course, since it's a 5-week course instead of a 16-week course, we were forced to squeeze in 3 weeks worth of work in each individual week. So I really wish we could have had a little bit more time together, even 8 weeks. I guess the attraction of taking a 5-week course is that you have, one thing is you have the rest of the summer, to enjoy yourself, right? So that's one good thing. But also, I think it's even possible to take a second 5-week course. I think isn't there another semester that starts next week? You can actually squeeze in a second course. I guess what the attraction is. For me, I'd rather teach it in 8 weeks. If we're going to do summer at all, I would rather do it in 8 weeks. But it's above my pay grade, unfortunately. So it's not my choice on that. I don't need to say that. Okay, so guys, if you have problems or issues or something like that, email. If you have places things you want clarifications on, please post them to the discussions board. If it's something personal matter, you can email me. But if it's something technical, something to do with the course, some clarification on a homework problem or something like that, please post them to the discussions board instead of emailing them to me for 2 reasons. Number one is then everybody gets the benefit from the answer to the question that you raised, and more often than not, they're going to have the same or similar questions if you've come across that. And the second thing is that if other students get to it before I do, they may be able to exchange information, and you guys can work it out on your own and not have to wait for me to happen to be able to log on at a particular time or something like that. So thanks for the 5 weeks we put together. I'm sorry that someday, you see my picture on there and stuff like that. Someday I'll be on the line at Panera and you'll come up to me and say, "Oh, Professor DeVito, I took your course in the summertime." And I'll have no idea who you are because I've never seen your faces. And that is way depressing, let me tell you. So if you do run into me, say hi and let me know that you took the course. And if you have suggestions on making things better, you can certainly bring that up with me as well. So if I don't have contact with you directly again, have a great rest of the summer. And please go back and make sure you get absolutely the most you can out of those homework assignments. Get 100% on every one of them so that that portion of your grade will really help you out. Okay, so good night, guys. And thanks for a brief but interesting semester.